This is applied physics course for undergraduate students, and today's talk is about the momentum, chapter 6. I am Dr. Nasir Mirza, and I will be discussing momentum, the linear momentum today. The linear momentum is a quantity which is a product of mass with velocity. For a body, the linear momentum is a vector quantity. It is given by P equal to m into v, where v is a vector quantity, and it has the same directions as that of the velocity. So the linear momentum depends on the frame of reference of observer. If we look into the Newton's second law, then it is also written as the rate of change of momentum of a body is equal to the resultant force acting on the body, and it has the direction of the force. That is as the sum of all the forces, which is the net force, equal to dp over dt, the rate of change of momentum. For a single object, we know very well that force, the net force, is equal to mass times acceleration, and the acceleration is the rate of change of velocity. So the dp over dt is the rate of change of mass times velocity. And if the mass is constant, then we can take out, and this is the mass time acceleration. Therefore, writing the dp over dt, the rate of change of momentum, is equivalent to mass time acceleration, the net force. The momentum is generally employed whenever we are discussing collisions in physics. Here I give you one example of collisions for the alpha particles that are colliding with the helium nucleus in a cloud chamber. And the shower of these alpha particles are going like this, and it is all these alpha particles are coming from a source, and the most of the particles are that are coming from the left, they are passing without a collision, but one collision is shown here, and it is visible. Alpha particle hits the helium nucleus, and then it is deflected to the other direction. So the particle trajectory of the alpha and the particle trajectory of the recoiling nucleus is shown here, and we can see the trace with the bright light. The collision has taken place and the momentum has changed. The initial momentum of the particle is now shown as with the new velocity vector of the alpha particle and with the new velocity vector of the nucleus. Such collisions and many other types of collisions are really the topic and the subject of the massive detectors that are used in CERN. For example, this is a proton-proton collider at CERN, and the particle physics research is done in this facility near the Geneva, Switzerland, and we can see the detectors. Here there are arrays of detectors that are going and they are placed in cascade manner, and the person standing is very small as compared to the region which is being enclosed by the detectors. From these detectors, the computer generated path of particle produced in one proton-proton collision is shown below, and you can see the showers of these particles going in many directions. But the most important thing is the collision and the collision's resultant shower of particles with the different types of momenta. The traces are that of the mass times velocity, the momentum that these particles are carrying in the chamber, the detector, and they are leaving the trace. Here we see the collision of a gigantic type where the two massive galaxies are colliding with each other. Simulation of such enormously large objects is the topic for the astrophysics. However, the many particle collisions and the fluid model for the galaxies are used to simulate the collisions, and uh, millions and trillions of the smaller size stars are the part of the galactic cloud. So the change in momentum and the transfer of momentum and transfer of energy is taking place in such collisions. We know very well when we are playing the billiard ball games, the collisions are of immense importance where we want to win. The ball hitting the other ball and transferring the momentum is the main object. Here you see the car collision that has taken place, and the direction of one car and the direction of the other car can be seen as a initial momentum before the collision, and now they are at rest. Both of them are at rest, but the collision has taken place. So collision is part of the physics of daily life. Here we show a bullet which is shot from the gun, and the bullet is going through the atmosphere, and it is generating an enormous profile of these shock waves. The shock waves of different types are making interference, and the shock wave is also traveling, and we can see the momentum, the original momentum, and we can see the high-speed bullet going far ahead as compared to the cloud which is generated after that, and the sound waves that are eventually enveloping the environment. Here we see that a nail is being stuck with the hammer, and hammers is used to uh, uh, give a large force to the nail for a very short duration of time, and therefore there is an impulse that is made available for such collisions, and the collision is again to transfer the energy from one object to the other, and therefore creating the new collision as a result. Let's come back to the linear momentum again and refresh that the linear momentum of an object of mass m moving with a vector velocity v is basically the product of mass, the scalar quantity, and the velocity, a vector quantity. In vector form, it is given as pxi plus pyj plus pzk as three components of the momentum vector, equal to mass times the vx velocity plus I unit vector along x-axis plus m into vy multiplied by j unit vector along the y direction, and m into vz times k unit vector along the z direction. Remember that the linear momentum has the direction along the velocity vector, and its dimensions are the mass, dimension of mass multiplied by length and divided by time. Its SI units are in kg, meters per second. The time rate of change of linear momentum of a particle is equal to net force acting on the particle. And that's the new form of the Newton's second law. So component of the momentum in x, y, and z direction are px equal to m into vx, py equal to m into vy, pz equal to m into vz. You see, momentum looks like similar to kinetic energy. Let us discuss both of them. Momentum and kinetic energy both have the mass and velocity. However, there are two uh, major differences between them. The kinetic energy is a scalar quantity, and the momentum is a vector quantity. Kinetic energy in conventional classical manner can be transformed into the other types of energy, where there is only one type of linear momentum, so they are not really similar in the transformations. Analysis model based on momentum are quite separate from those based on energy. The kinetic energy model has half mv square in the classical physics. It's the relationship with the velocity and mass. So it's a nonlinear function of velocity, and it is proportional to mass. The difference allows an independent tool to be used to solve the problem if we want to solve problem with respect to momentum or with respect to the energy. The conservation of momentum is really at the heart of all these things. Let's see this Archer's example. Archer is standing on a frictionless surface, that is ice, and the approach is that we consider no motion. So no information about the velocities is available. Newton's second law is not applied, then no information about the force or acceleration can be obtained. And if the energy approach is not adopted, then no information about the work or the energy can be asserted. However, if the momentum information is available and we know the momentum uh, given to this arrow, and then we can assess how the person will slip and how the momentum change or the conservation of the momentum will dictate the velocities. So in solving such problems, the total momentum before realizing that the arrow is released is zero. So the total momentum then after releasing the arrow will be equal to zero. So this will be the final momentum of the one arrow and the final momentum of the man. So the final velocities of the archer become negative. They indicate that he is moving in the direction opposite to the arrow. An archer has much higher mass than the arrow, so its velocity is much slower. So the conclusion is that the problem seems very simple, but could not be solved using the previous analysis models. We use this new momentum model to find the solution. And if we do this, the solution is quite simple and straightforward. Let us briefly talk about the impulse and the relationship with the momentum. Momentum of an object changes when a net force acts on the object. According to the Newton's second law, the force is equal to the rate of change of momentum, or the change in the momentum dp is equal to force multiplied by dt. So if the momentum of the particle changes from pi at time ti to p final at time tf, then delta P is equal to the change, the final momentum minus the initial momentum, which is equal to the integral of this force with respect to time from Ti to Tf. The quantity, this integral of force F into dt integrated from Ti to Tf is basically the quantity termed as J. It depends on force, it depends on delta T. So this quantity is called impulse. It is impulse of the force. Roughly speaking, the impulse is equal to the force multiplied by delta T, or the average force is defined as 1 over delta T times the integral Ti to Tf, F into dt. So the impulse of the force acting on a particular particle is equal to the changes in the momentum from final, from initial state to the final state. If we employ the Newton's second law in terms of the momentum, we say that the net force delta, the net force, the sigma F, is equal to dp over dt, which means the rate of change of the linear momentum. So change in momentum is basically F into dt, the sum of this product. Then the total change in time from Ti to Tf is given by this F, the net force, integrated over the time, which is equal to dp, which is equal to Pf minus Pi. Therefore, the impulse can be safely said as a J net equal to sum of all such products where the integral of F dot dt is taken. The momentum of the system changes when the net force from the environment acts on the system. And for momentum to be considered, a system is non-isolated if net force acts on the system. So change in momentum of the particle is equal to impulse of this new force acting on the particle. And it is from Pf minus Pi, which is J net, or the impulse, or the net impulse. This is equivalent to Newton's second law, which says that the change in momentum under the interval delta t time is given as F dot dt, sum over all the forces. So this is mathematical statement of a non-isolated system having momentum model, and this is telling us about the change in momentum. The change in momentum is equal to the J net, or the impulse, and the impulse can be expressed in scalar components as 3 scalar components: x component, y component, and z component, which is delta px, delta py, delta pz. And in fact, it is the final minus the initial momentum along x-axis, final minus initial momentum along y direction, final minus initial for the z direction. We can also tell that this is the impulse, which is the average force multiplied by delta t. So J net is average force multiplied by delta t, or delta P is equal to the average force multiplied by delta t. Here we show that the force as a function of time increases, and then keeps on decreasing. So the area under this curve is basically the J. But we can have the same area as if we use the average, F average, multiplied by delta t. So equivalent to the area, which is the red colored area, can be made through this simple approximation, which is the F average into delta t. Let us do one example of a baseball. Baseball which is uh, 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 thrown, and it has an official weight of about 5 ounce or a mass of 0.14 kg, which is moving horizontally at a speed of 93 miles per hour, which is approximately 42 meters per second. Pakistan's fast bowler Shoaib has been seen to throw the horizontal ball at the speed more than 102 miles per hour. Uh, so this speed is relatively low as compared to the bowling of Shoaib Akhtar. Now, this is the speed at which the ball is stuck by the bat, and it leaves the bat in the direction at an angle 35 degrees and with the speed of 50 meters per second. The initial speed was 42 meters per second. The final was the 50 meters per second. Question is, find the impulse. Impulse of the force exerted on the ball. And the then second part is, assume collision lasts for 1.5 millisecond. What is the average force? And then finally find the change in the momentum of the bat. So let's do the first part. This diagram shows the directions and the vectors of the momentum. The initial momentum is shown here as Pi, and the final momentum is shown as Pf. The Pf is at the angle phi, which is equal to 35 degrees. So Pf can be decomposed into two components, one parallel to x-axis, other perpendicular to x-axis. The parallel to x-axis will have the Pf cos of phi, and perpendicular will have Pf sine of phi. Then let us find out the initial momentum and the final momentum. The final momentum is m into v f cos of phi we can calculate. And the final momentum y component is m into v into sine of phi. And by substituting the mass and the velocity, we can find out the final velocity. We can find out that the final velocity, the final momentum is 4.0 kg meters per second. The initial momentum is along the x-axis only, and it has a value of m into vi, where m is 0.14 kg and the velocity is minus 42 meters per second. Minus is due to the fact that this is the direction of negative x. So we calculate the P initial, and then we have the P final, and we find out Jx, which is delta Px equal to the final momentum along x-axis and the initial momentum along x-axis. And we find the answer 11.6 kg meters per second. Similarly, the Jy is the delta Py equal to mv final minus mv initial for the y direction, and we come to know that its value is 4 kg meters per second. Now we know the two components of the J vector, Jx and Jy. Therefore, we can find out the magnitude of J equal to Jx square plus Jy square under root the Pythagoras theorem. And by substituting these values, we get the 12.3 answer. Then we go for the angle. What will be the angle of this vector? Its angle is theta, and tangent of theta is Jy over Jx equal to 4 divided by 11.6 and you get the value of 0.3448, taking and the the inverse of the tangent, we find the angle equal to 19 degrees. So the information about the J is complete. J vector has now the magnitude and the direction. Now comes the another part where, assuming the collision lasts for 1.5 milliseconds, what will be the average force? So we move forward, and now the average force is given by the impulse. The average force is equal to impulse divided by delta t. Now we know the impulse, the vector, it is 12.3 kg into meters per second in its magnitude, and divide by the delta t, which is 0.0015 second, and the answer is 8,200 newtons. Now this is really large force. And we are quite safe in assuming that the impulsive force is great as compared to the external other types of forces, such as gravity, and therefore nearly it is equal to the net force acting on the object during the collision. Change in momentum of the bat is given by the Newton's third law. Newton's third law says that the force exerted on the bat by the ball must be equal to the force on the ball by the bat. So the bat has delta px equal to minus 11.6 and delta py equal to minus 4.0. And this is just the opposite change in momentum of the ball. And that's how we find out the complete answer for this example. Let us do this one more example to amplify our ideas of the linear momentum in a particular crash test. A car of mass 1,500 kg collides with a wall. As it is shown here, the car is coming and colliding. The car has initial and the final velocities as minus 15.0 I unit vector meter per second and 2.6 I unit vector meter per second, respectively. The collision lasts for about 0.15 second. The question is to find out the impulse which is causing this collision and average force exerted on the car. If we go for these two things, first of all, look at the vector. Minus 15.0 meters per second is the initial velocity, and the final velocity is in the other positive x direction, and positive x direction is giving us 2.6 meters per second. So the vector is small as compared to the initial vector. So we find, first of all, the initial and the final momenta of the car, Pi equal to m into Vi, which is equal to the mass, 1,500 kg, into minus 15.0 I unit vector and meters per second. So the answer is there. And similarly, the P final is 15 kg, 1,500 kg multiplied by 2.60 I unit vector, and the answer is there. The impulse is given as, because it is horizontal, therefore there are no other components of the velocity. The impulse is given as J equal to delta P, which is m into V final minus m into V initial. And we substitute these two values and get the answer equal to 2.64 into 10 to the power 4 I unit vector. It is in kg meters per second. The average force exerted by the wall on the car is then given by F equal to the average F equal to delta P over delta T. Now, delta P is the impulse which is known to us 2.64 into 10 to the power 4 I unit vector along the positive direction of x-axis. So this is the force divided by this time delta T is 0.150 seconds. The answer is 1.76 into 10 to the power 5 into I unit vector in the Newton. Now, if the car did not rebound from the wall, what will happen? Here we see the car rebound, which is plus 2.6 meters per second. So the vector, the momentum vector is going in this direction, and then there is a rebound, it bounced back, and you had 2.60 meters per second. But if this was 0, then we will see that the PF will be 0, and the J will not be this much large. It will be smaller. Its value will be small, and the force will be less. So suppose that the final velocity of the car is 0 and the time interval of the collision remains at 0.1. Will this represent a large or the small force? So we now know that the delta P will reduce for the same time. Therefore, the force will reduce. So if there is no bouncing back or rebound, then the car will just stop there, and the exchange of momentum to give a larger force will not be there. Force will be small. The net force, the net average force will be small. So we stop here this lecture, and in our next lecture, we will continue our discussion about the linear momentum, the chapter 6, and its part number 2, which will be primarily about the collisions and the effects of the collisions. Thank you so much.